substituting the values of A and B in equation number 1. Let's see what we are going to get. So we'll get C of S. A will be, here A is T square. You can see this equation. A is T square divided by 1 by ST. So this will be T square divided by 1 by ST. Then we have B plus the value of B is minus T. So that will be C value was 1 plus minus TS. Okay, we write it here. 1 minus TS divided by S square. So let us simplify it more. So I can write CS as, CS can be written as 1 by S square. I will write first. Okay, S and S will go, and that will be minus T by S. Minus T by S. And in third case, what we are going to write, this is T square, not T2, sorry. Okay, this is T square A value. So third we will write like this, plus T square will be in the numerator. I'll take T common. So this will become S plus 1 by T. So square and one of them will go. So finally the C of S will be in S domain will be 1 by S square minus T by S plus T and T gets cancelled. That is T by S plus 1 by T. So let's take the Laplace inverse of S, because we have to make suitable arrangements in order to arrive at the Laplace inverse. So taking a Laplace inverse of above equation, we have, so that will change to time domain T. 1 by S is for a ramp. Then in time domain, ramp is represented by T minus 1 by S is step. Time domain, it is represented by 1. So T multiplied by 1 is T plus capital T multiplied by e raised to power minus T by T. Sorry. Okay, minus T by T. So this is the response which we have got when we have used the step input. So let me put it in the red. Very important result. Okay. Okay. Now if I have to find the error is always input minus time domain. I will find the error. The error signal we know. Error signal is E of T, and we have done it in the first chapter also. Will be, error signal is always input minus output. That is R of T minus output is now in time domain C of T. So input to this is T, because it's a ramp input, minus output is T minus T plus T into capital T into minus T by T. So T and T gets cancelled. So error signal T gets cancelled with T. So error signal is plus T minus T e raised to power minus T by T. In other words, it will be T will be common, capital T, 1 minus E minus T by T. Now after that, what we are doing, we have seen in the network also. Let's talk about because we are interested in the steady state error always. We are not interested in the transient what's happening. Once the response settles down, we are interested in the steady state error. Now steady state error here will be Steady state error is limit t will tend to, because we are talking about a steady state, so it is infinity, t minus t into e raised power minus t by t, which will be equal to t tends to infinity, e raised power minus infinity is 0. This term will become 0, so it will be t. So, what is the steady state error? Steady state error is equal to t, where t is the time constant of the system. So, steady state error is equal to t, and t we know t is a time constant of the system. Time constant of the system. Okay. For smaller time constant, what will happen? Steady state error will be small and the speed of the response will increase. If t is less, the value of t is less, then what will happen? Time constant will be small, and with this case, the speed of response, as the time constant is less, speed of response will increase. That is, whatever the response we are getting, that speed is going to increase. So this is about this. Let me draw this, if I need to draw this, and so that I can show you. Now let's talk about ramp input now. Okay. So what we have here, now your actual output C of t will start a bit like this, and then it will have to rise okay like this. Now if we are talking about the steady state response, let me make this another color for you. Now steady state response, we expect that steady state response is like this. Okay. And now this is what? This is your C of t. This is your error. Okay. So if you see this, and this is your time constant. Let me, so let us say this is 2t, this is your time, this is your response. But what is the input? Input is r of t. Okay, this is the response we are getting here. Input is r of t. Let's say this is 2t, 2 time constant. This is 4 time constant, and this somewhere is 6 time constant. And here we have 2 time constant on this side, 4 and 6. Now, after plotting this time t versus the response, having giving the ramp input, so this is what you are, this is a steady state error. Actual response you expect to be like this. This is the actual desired response. Sorry, this is your actual response C of t, what we are getting. So this you can say is your actual response, which we also treat as input. That is, input minus output is error. That is input. Actual desired response should be this one, but we are not getting it. We were getting somewhat error, which is like equal to small t. Okay. So this all here is equal to t. This error is equal to t. So this error is here like this, and then sorry, like this error is value t. So this is what, this is basically a unit ramp response of the system. So very clearly, what is the input? What we should get? We should have normally got this, but we are getting a delayed at the beginning. Then we transient periods are delayed. Then it rises and gets a final value of this one. It's the actual output. Input minus desired output minus actual output should be equal to error. Error we are getting. So this is what is for the unit ramp response of a system. Now response. Now next is response. Is it clear or not? हाँ जी तंजीब. Not
Clear,
clear?
sir, clear.
Okay. Next. Response of the first order system with unit impulse. Okay. Input in unit impulse is 1. Input is unit impulse function, and that is Rs in the S domain is equal to 1. That we know. Okay, we know now. We are continuing with the same. We are substituting, we'll be substituting the same input here. CS is R of 1 plus S plus T. This is the basic. Okay, response of the system ramp. Earlier we have also done it. So now instead of ramp, it will be unit impulse. So we'll continue with the same transfer function. So we know C of S divided by R of S is equal to 1 divided by S plus T plus 1. So therefore C of S is equal to R of S multiplied by St plus 1. So C of S in this case will be equal to R of S is 1. We know that R of S is 1 because, let me put for your information, R of S is basically a delta T, and R of S will be equal to Laplace transform of delta T that we have derived earlier. It is equal to 1. This is for your information. So 1 by S T plus 1, it will be multiplied by 1. So what we can do here for taking the Laplace inverse, we'll take t common, that will be s plus 1 by t. Now taking the Laplace inverse of this one, taking the Laplace inverse, c of t will be equal to 1 by t into e raised power minus t by t. And obviously this will be for greater than t greater than 0. So this is, let us call this one equation number 2. So I will draw the curve also and I'll explain. The curve of equation 2 will be shown in the figure. I will draw it. Comparing equation C of t equation C of t equal to 1 minus e raised power minus t by t. This was response. Okay, comparing the equations, this was for unit step. Okay, and this response for was ramp. Just now we have done it, and this response is now for which one? This response is for now unit impulse. Step, ramp, and unit impulse. So what we can write here, we can draw an analogy here. For unit ramp, input R of s equal to 1 by s square, that we know. Then response in the time domain is this, t minus t plus capital T e raised power minus t by t. For unit step, input R of s equal to 1 by s, c of t is equal to 1 minus e raised power minus t by t. For unit impulse, input R of s is equal to 1, then c of t will be equal to 1 by t e to power of minus t by t. Okay. Okay. From above three equations, it is clear that unit step input is the derivative of, you can see here, unit step in derive, take the derivative of step with respect to t. This will be 0 minus e raised power minus t by t into internal derivation, that is minus e raised power minus 1 by t, minus minus will be plus. So first it is clear that unit step is the derivative of unit ramp. We can see that also. First we will write unit step is derivative of unit ramp. You can very clearly see if we are taking unit step, ramp take the derivative with respect to t, 1, so minus, this is a constant 0, plus t e raised power minus t will be minus t e raised power minus t by t into derivative of this, that will be minus 1 by t. So it will become 1 minus e raised power minus t by t. It's very clear here. Okay. Okay, unit step is this one. Next is, if we take the step derivative, if we are going to take the derivative of the step, then we can see that this is 0, minus will be there, e raised power minus t by 2 into internal minus 1 by t, minus minus will be plus 1 by t. So unit step is a derivative of unit ramp, whereas unit impulse is a derivative of unit step. Okay, I think this is clear. Okay, then this was the first thing. Thus, we can also say that the response to the derivative of input signal can be obtained by differentiating the response of the systems to the original. That means we can take the response, we can take the derivative of ramp, we will get step, we can take step, derivative of step, we will get impulse, and so on and so forth. This property is very important for the linear and time invariant systems. So this property is very important for the linear and time invariant systems. So I will draw the graph again to explain this. Okay. So now you can see this is the response C of t, or unit impulse response of the system I'm talking about now. Just now we have done it. So here I can say, here you can see we're talking impulse. So 1 by t is there. but then the function is decaying exponentially. This is decaying, so exponentially it will rise to some function and it will start decaying like this. Okay, curve is not so smooth because I don't have anything to draw the curve. So this should not be like this here. It should be, sorry, it should be a smooth curve. Okay. Okay. So let us say here, this is 1 by t, because if we take the value of this e raised power minus t is equal to 0, this maximum value will be 1. Okay. When the maximum value will be 1, the value will be 1 by t at the maximum. Then if we put it t, and then we can put it 2t, value of the time, and then we can put it 3t like this, and somewhere here when we response reaches we can take it 4t. So with t it will be e raised power minus t, and then value will be, sorry, value will be somewhere here. If you put capital T here instead of small t, e raised power minus 1, so value will be somewhere here 0.37. It will go on increasing, and finally at 0 it will reach 1 by t, and so it will start decaying exponentially from 1 by t value to somewhere it will, when it will be 40, it will reach to somewhere the value will be equal to, this value will be equal to, on the x-axis would be 40, and it will be maximum at 0. You can see it is origin here. Okay, maximum at origin, then it will keep on decreasing 0.37 and so on and so forth. You can calculate those values, and it will exponentially decay. At 40 it will settle down to on the x-axis, that is time axis. So this is the response we expect for unit impulse response of the system. Okay, so this value is c of t 1 by t e to power of minus t by t. So you can substitute the different values and you can get this curve. So I'm highlighting this curve here. So this is very important for us, this curve. Same curve, okay. So this curve you can get, that is clearly an exponentially decaying function. Okay. So that's all for the 3 types of responses we have. So we have got these responses. The next will be, just a second, I will copy this numerical. Small numerical is there. Okay. We copy it here. Space here. Okay. So we have a numerical here. Find the capacitor voltage in the figure shown, in the network shown in the figure. If the switch closes at equal to 0, assume 0 initial conditions. Also find the time constant, rise time, and settling time for the capacitor. So our network is like this. Sorry. Network is like this. Okay, so this is your DC voltage source. This is your switch. Okay, then at t equal to 0, this should be the situation. Switch will close like this. Okay, this is your resistor. Sorry. Okay, this is your capacitor. This is your capacitor. Okay, the value of this is 1 by 2 farads. This is 5 volts. And t equal to 0, switch is going to close, and this is 1 ohm. So let's draw the Laplace equivalent of this. Laplace transform will draw. Okay, so let me copy this figure again. Okay, copy, paste. Okay, switch at t equal to 0 is going to be closed now. So we'll close the switch. This values will also change. So at t equal to 0, this switch is going to be closed. So now what we will doing, we'll be closing the switch now. So 5V Laplace transform of this is 5 by S 1 by current. Let's say current flows will be now I of S in the loop, and then 1 by C of S, that will be 1 by 2 of S, because farad value is 1 by 2, so that will be 2 by S. This value comes out to be 2 by S, and 1 will remain as it is, 1 only. So let's apply the KVL to this loop. Very simple. So what will be plus 5 by S? Okay, sorry, minus 5 by S first. So that will be plus I of S into 1. Okay, plus I of S into 2 by S will be equal to 0. So we have here I of S will get common. S plus 2 by S, this will be I of S will be S plus 2. Okay, that will be 5 divided by S plus 2. So IFS will be like this. So if we have to find what is our aim to find? Also find the time constant and this. Okay. So voltage across this voltage source we can find this across the capacitors only. Let me check the original diagram if there is capacitor voltage. Okay, no. Okay, what we need to do, the let's find the voltage across the capacitor, because we'll see this time constant with respect to the capacitor. So let's say the voltage across the capacitor V naught of S, call it equation number 1. Let's say this is V naught of S. Here we can write this voltage is V naught of T. So we can find here V naught of S. Okay, so V naught of S will be, what will be, current multiplied by that value 2 by S. So current is I of S into 2 by S. So therefore V naught of S, sorry, V naught of S will be, this we have to multiply. So that will be 5 divided by S plus 2 multiplied by 2 by S. So this will come out to be 10 divided by S into S plus 2. So V naught of S value is this. So now again we have to find the partial fraction for this one. So we can write 10 divided by s into s plus 2 will be equal to, okay, that will be 1 by s plus 1 by s plus 2. So we can further write 10 will be equal to, multiplying by the denominator, this will be s plus 2, okay, plus s. So it will be, value will be like this. Sorry, it will be a divided by and b divided by. So a into this and b into this. So substitute the value of s is equal to 0. Let me page. So put s is equal to 0. Therefore 10 will be equal to a multiplied by 2, and that will, a will be 5. Put in second case s is equal to minus 2. Then 10 will be equal to b into minus 2, and then b will be equal to minus 5. So we can substitute this value in C of s. C of s can be written as, that is equal to 10 divided by s plus, so that is equal to a by, a is what, 5 by s minus, that is 5 divided by s plus 2. Okay, so taking 5 s, we can take common, 5, sorry, we can take common, 1 by s minus 1 by s plus 2. So taking the Laplace inverse, of above equation, Tanzib,
Yes, sir.
send me log, abhi log bhejo.
Okay, sir.
Okay, C of t will be equal to 5, that will be minus 1 e raised to minus 2t. So that's the answer. So now, first what we have to find, we have to find time constant. Time constant is real value. So that is the real pole, 1 by a. Real pole is 1 by a, that is 1 by 2. That is 0.5 second is the time constant. Next, rise time. Rise time value we have already derived yesterday, 2.2 divided by a. 2.2 divided by a is 2, so that is 1.11 seconds. Third is settling time. Settling time is T of s, which is 4 by a. Rise time is tr. Okay, 4 by 2, that is 2 seconds. So very simple numerical for the first order system. So we have got the capacitor voltage, and then we have found all other values. That's all. Okay. Now let's talk about second order system now. So here, just a second. Okay. Now let's talk about the second order system. Any doubts in the previous question? It's very simple. Let's have an introduction to the system. Okay, I will explain this one by one case, but before there will be some explanation. Just a second. Okay. Okay. Introduction to the system is, now what we need to do, we need to extend the concept and poles and zeros and transient response to second order system. Sorry. Okay. So concept we need to extend, concepts of poles Then we have zeros and transient response. These are three important things. So concept of these, we need to extend it to the second order system. Concept of poles, zeros and transients need to be extended. Extended here means, it means we need to more explain these concepts on the basis of when the system will be second order. The poles can be imaginary poles, poles can be real poles, poles can be completely imaginary, conjugate poles. So then we have to see what type of response we are going to get. Need to be extended to second order system. Order system. So now these things we need to explore to second order system. Okay. Now second order system will, it will have a wide range of responses. That means second order system will exhibit, or it will have, second order system will not have only few responses, but it will have wide range of responsible. Second order system will have wide range of responses that we have to see by taking an appropriate example. Okay. Now, first order system we have seen parameters in this case, when we are changing the, when we are varying the first order parameter, that means system parameters or poles we have seen last time, that will change the speed of the response. The first order system is limited to the extent that if we are varying parameters, we are varying parameters in first order system, then it's what it's also, it's only going to change the speed of response. So it is going to change the speed of response because the variety of responses are limited in this case. But in contrary to this, the changes which we make in the parameters of the second order system, it will change the form of the response. So changes in the parameters of second order system will do what? It will change the form of the response. It will change the form. That means type of response it can change. It can change. I'll talk about that. There will be exponentially decaying function. There can be sinusoidal oscillations will be included. So number of things will change in this case because the variety of the responses are in a bigger range as compared to the first order. So it will change the form of the response. You have to mathematically see, and then physical interpretation is also very important in this case. So second order system can have different types of responses, and then characters of that will be different. It can be like the first order system, but it will depend upon the component values, what are the values of the poles and zeros, and it can also display. So second order system, what I'm telling, can display characteristics much like first order system. There will be no problem, but that will wholly depend on the component values. But it can display damped or pure. We can see it can display second order system. Second order system is also going to display damped and display damped or pure oscillations. Which type of system? That should be obviously transient, because the transient system only, there will be some variation, there will be some changes. Finally, the steady state will settle down at some value. So that will be for its transient response. So that we have to see. I'll again repeat that second order system, what is the difference? If we vary the parameters, it can show you, it can display the characteristics, or it can show you the characteristics much like the first order system, but that will depend on the values of the components what we'll be using, poles, and then what are the values we are using. And it is also capable of displaying damped or pure oscillation, that we'll see in the coming lecture. So for that, what we are considering a numerical example of the second order system. Like I have taken the numerical example here. In this numerical example, what we are doing, all the examples, all the responses will be derived from this first. This is the figure number A. The A, figure number one, A. A is the input, step input is there. Then we have transfer function, and then we have output. So this is our basic response. So all examples are derived from this. We call it a general case, which has two finite poles. It's a second order system, S square plus AS plus B, two finite poles, and there will be no zeros. So what are we sorry, let me write this in general form. General form is like this, what I am considering. General form is like this. Okay, this is a general form where we have RS, and I told you RS will be taking a step response, and then general form is B divided by, this is the general second order system we are considering, S square plus AS plus B. So this is a general second order system we are considering. Out of this, by varying the values of this B will be a multiplying factor. I will explain this. Okay. So this is a general second order system we are considering. So what we are doing in this case, it's having general second order system. You can very clearly see there is no zero in this case, no zero, but there are two finite poles. That means there are two poles. Finite means number is there. There are two poles. If you do not want to use the word finite, that means two poles are there. Okay, this is the one thing. The term which is in the numerator, the term in the numerator is B. What is the term in the numerator? That is the term is the B. It's a multiplying factor, or we call it a scale. That means it will have a number that can multiply something. We call it scale or a multiplying factor. Multiplying factor that can have any type of value, that can take any numerical value, and by taking any numerical value, it will not affect the form of the derived result. Whatever the results we will derive, it will not have no impact on that. I'll explain it again. The factor B which we are considering in the numerator, so that will be considered as a scale or a multiplying factor. But that multiplying factor which we are considering, which we are taking into consideration, will not have any effect, or it will not influence the form of the derived results. Whatever the results we are deriving, it will not have any impact on that. That should be very clear. We will assign appropriate values to A, B. Now there are A, B in the denominator, constants. So we are going to assign, or we are going to put these two values appropriately. We will assign appropriate values of, for parameters A and B, we are going to assign some value that should be appropriate, that should not be approximate. Why? Because then while we are assigning, or while we are assigning the appropriate values, while we are substituting or putting in appropriate values in the constants A and B, then what we are doing, we can show all possible second order transient responses. With this, by assigning the appropriate values to the constants A and B, we will be able to show all possible second order transient response. That I will tell you one by one. So I'm explaining again. Number B, we are taking a general example here. B is a multiplying factor. And with this multiplying factor, whatever we are using, what are the derived results will be, what are the results we'll be getting, it will not have any impact on the response. And then by substituting the appropriate values for the constants A and B in the denominator, that will allow us to explore all the possible responses in the transient responses, whatever the possibility will be there for the responses, that will explore us to exhibit those type of responses. That should be very, very clear. The unit step we know can be found by using C of S will be equal to, we know this formula already. We can use C of S is equivalent to R of S into G of S. That means transfer function multiplied by input. And we'll be considering here for the sake unit step. Then you can extend to all other inputs again. Okay, that you can extend to all other inputs again. So what should be our mode of operandi? What should be our operational mode? How we can solve this? The unit step response we will find by this, and it will be followed again by the partial fraction. We'll be using the same partial fraction method, and once we are able to do partial fraction, and we'll take the inverse Laplace. Now in this case, we can explain now each response, and we can see how the poles, what are the poles there, how they will determine the nature of the response. So from the poles, we should be able to we can find the response by considering, we can use the poles to determine the what, to determine the nature of the response. This is also one technique, without going through the tedious calculations of partial fraction and inverse Laplace. That also will be, we don't have to go to the tedious calculation like here I'm explaining, that we have to find out partial fraction then inverse Laplace. But if we know, we can see how we can use, or we can explore these poles, and then how we can determine the nature of the response. And in that case, we should not go through the tedious or a difficult calculations of the partial fraction. We'll find first, and then we can find the inverse Laplace. So without that, we can also do. Let us consider the first case here now. Now, what we are assigning in the first case, I'll write it here for your information also. Let's consider first, we are considering the case of overdamped. What are the possible responses? I will be writing that. Number one is an overdamped response. Okay. Now, overdamped response, it is in the, overdamped response is in the figure 1, we are showing it, and in the number B. A is general, B, you can see here, B. What is there? I will write it here. I will be drawing it again here. Okay. Now in figure B, what we are showing that R of S is what? Here, you can go back to this figure. R of S is 1 by S. So input is always, we are talking about a step input only. I have talked here about that. So R of S will be 1 by S. In that case, A we are assigning 9. 9 divided by, this is your step input transfer function, and S square plus A as 9 and B also 9. And this is your expected, C of S. Okay, I should not write 1 by S. We'll multiply that 1 by S. This is a transfer function only, sorry. Okay, this, no need. Okay, so this is C of S. Have a look here. What we have changed. Now, general was B divided by S square plus AS plus B. So A equal to B is equal to 9. So this parameter is the first manipulation we are making in the constants. A is equivalent to B is equivalent to 9. So what we are expecting now, if we go through this, now we will get a response. We will get a response. What will be the response? Let me write it for you. Then we'll go to the other things. Now response here will be input multiplied by the transfer function. CFS will be input, that is 1 by s multiplied by s square plus 9s plus 9. Okay. Now let me make the roots of this s square plus 9s plus 9. We can use equal to 0. Then we can use s is equal to minus b, that will be minus 9 plus minus under root of b square will be 81 minus 4ac will be 36 divided by 2a, that will be 2. And this will come out to be s is equal to minus 9 plus minus 81 minus 36 will be, I think, 945. Yes, 45. So that will be 5 into 3 into 3 divided by 2. 15 threes are 45. Yeah, 45 plus 36 is 81. So here I am getting s. There will be two possible roots. That will be s1 and 2 will be. I will be writing. You can calculate that. That will be 7.854, one of them, and next will be 1.146. Okay, so I can write this C of s here. C of s I will write like this: 1 divided by s. So s minus 7.854 multiplied by s minus 1.146. Okay, so two roots I have got in the denominator. Now have a look. Once for all, you have to remember these things what I am telling. This function, very clear. From here, later on, I will talk about the graph. Later on, we'll talk about the graph. Okay. This function is having what? This function, above function, I'm talking about this function. Let us call it equation number 1. Now, this function has what? This has pole at origin. It has only pole, so this is pole at origin. This is pole at origin. Okay. So where from it comes? That comes from the unit step input. So unit step input. So pole, this function has a pole at origin that will come from the unit step input. And second, it has got two real poles. You can see it's a real poles. This is a real pole, no imaginary part here. So
No, minus आएगा minus 1.46.
yes,
Minus 1.46.
okay, no problem. Minus. It is minus 9 minus something. So minus or plus, sure.
Minus, sir.
Okay, no problem. But still they are real. It's a negative real axis. It's the roots are still real. I'm not worried about the calculation right now. I'm worried about the physical interpretation right now. I want to explain the graph, what's happening to the function as a response of the second order system. So I'm worried more about, not about the calculations. Please make sure. Maybe it's minus, but I'm not sure. Okay, I have just calculated here and I have put the value. You can change it, then it will become plus. You need to check it, please. Okay. So this should be also plus, I think. I think both are minus, I think. Then both are minus. Yes, you can check it, no problem. Anyway, so number one, I have talked that one has a pole is at origin that will come from the unit step input, and two real poles are there. Two real poles are there that will come from the system. So please go through that system poles, input poles I have talked about in the last lectures. Those terms should be clear. Whatever I am explaining in the previous lectures, they should be clear. So two real poles that will come from the system itself. System means from the transfer function. Okay, the two real poles that is from the system. The input pole at origin generates constant force response. So this will generate constant forced response that I already talked about last, force and natural response. So input pole at the origin will generate a constant force response. And each of the system poles, that means which are the system poles, we have each of the system poles that will on be on which axis? Each of the system poles will be on the real axis. They will generate an exponential natural response. So each of the system poles, that is system poles which come from the transfer function, what they will be doing, each of the system poles will be on the real axis, and please make sure here they will generate natural response that everybody knows, that even in network, network I have talked about this, that will generate a natural response. But here an addition will be that will generate an exponential, that will generate an exponential natural response. That will generate an exponential natural response. Okay, we'll talk about this in the next lecture. See, we need a clear explanation क्योंकि आज आधा हो जाएगा कल आधा, तो we'll talk about more from this only. So for the time being, we have reached to the second order system where we are talking about the first response, that's an overdamped response. Okay, so let's stop today here only.